Okay, so welcome back, everybody. And the session today is going to have a focus on the mathematics of recurrent neural networks. And one of the reasons for that, although many of you may actually use PyTorch and let's say TensorFlow and/or TensorFlow, is actually to give you some of the gritty-nitty details behind the algorithm, which is called backpropagation through time. So in a way, this is going to be a lecture where we mainly use the slides. So I hope I'm not putting everybody to sleep as quickly as possible, but that you can follow me on some of the basic ingredients here. And then we are going to look at how you can build up your own code based on the equations. So we did the same with the convolutional neural networks. And many of you have seen the same when it came to neural networks. And recurrent neural networks, convolutional neural networks, and neural networks, understanding the basic mathematics is something which I think is useful, because these methods, they enter as building stones in other methods, like if you're dealing with autoencoders, which we will start looking at next week. Then you will typically see that people have internally in an autoencoder something like a neural network or recurrent neural network. If you're dealing with the energy-based models, which are parts of what we call generative models, which we will start looking after the middle of March, roughly, then you will see that in these energy-based models, which are also often called Boltzmann machines, because you have a probability distribution which looks like a Boltzmann distribution, then the argument to the exponential function can be a convolutional neural network or recurrent neural network. And this has been a very successful way to generate, let's say, new data, or if you use CNNs, to generate new images. So we put some emphasis on the mathematics so that you can, if you want to, you can build your own code. We have people here who want to look at language models, and in natural language processing, the recurrent neural networks were actually some of the first type of models which have been devised and used. So looking at the recurrent neural network as an entry point to, let's say, language models, language processing, is something which I think can be useful. So in a way, looking at the mathematics, which at a certain, if you want to be a little bit arrogant, this is just the application of the chain rule again and again. And you have more complicated, convoluted matrix vector multiplications. So I'm going to baby step you through the ingredients, and then we're going to look at applications. And the type of applications we are going to look at is, one is weather forecasting. And you will see that it's not doing too well there. And then we are going to look at the differential equation, which we looked at last week, the plane harmonic oscillator oscillations with and without friction and with and without an external force. And then we are going to look at the classic MNIST data. So in this course, you will see the MNIST data being used again and again and again, because this is a kind of benchmark set of data. Now, I wanted to remind you first of where you can find codes. So in Rashka's textbook in chapter 15, there is a discussion of implementing recurrent neural networks with PyTorch. And that's something which I normally recommend. And same with David Foster has in his textbook in chapter 5 on regressive methods. There is a Jupyter notebook which implements a recurrent neural network using TensorFlow. So then you will get examples from both worlds, either PyTorch or TensorFlow. But we will, in this case, we will also have our own code. So in case you want to have a project where you just do one method, where you use the whole semester to, let's say, implement your own RNN, or as we provided some weeks ago, 2 weeks ago, to write your own CNN code. Any questions so far? So I also want to remind everybody that we, if you want to do one project, please let us know. And then the only thing you need to do for the deadline of March 21st is just to upload a one-page summary of what you want to do and where you are. That okay? Okay, that was the messages. So let's, what I wanted to do is to give you just a quick top-down view, like we discussed last week. Now, last week we wanted to keep these things at a more top-down view. And that means that the kind of insight you get is hopefully the top-down one, but it can be superficial. So now we're just going to go into some of the details. But I wanted to remind you of some of the overarching top-down views of recurrent neural networks, which we also discussed last week. So a recurrent neural network, as opposed to a regular fully connected or just neural network, has layers that are connected to themselves. And when we are going to look at the details of the code, you're gonna see these differences more clearly. So these work very well with sequential data. One of the drawbacks is that it's particular for the back propagation through time algorithm, is that it is very expensive when it comes to number of cycles. And it requires also you storing a lot of information about the weights and the biases for the different time steps. So when I use the wording time, it doesn't need to mean literally time, but this is a sequence of data which are ordered in a specific way. So this could be you making an approximation to calculations of integrals, where you have 10 integration points, 100, 1,000, etc. And then you want to extrapolate to an infinity of integration points. So then you could think of you having sequential data on a log scale. 10 points, 1 in log scale, etc., etc. So that's also one way to use recurrent neural networks. So you would fit to some initial points, and then you use these points to extrapolate to, let's say, infinity. So if we now look at these methods, the kind of things which we did last week was to give a graphical representation. So typically a neural network would be you having some inputs. This goes through some hidden layers, and then you have some output. Whereas now the recurrent neural network, you have some input at a given time t. So this could be some external probe which you apply to, let's say, a specific experiment. Could be you measuring, as we mentioned last time, the blood pressure of a patient, a series of patients, and you would measure the blood pressure, let's say, every day, and just then use a recurrent neural network to eventually make an extrapolation. And this kind of circle or kind of blob here is now representing, when you open it up, it's now representing all these hidden layers. Now, as I said, this looks a little bit superficial, but it's giving you the basic message of the structure, so that in here you would have different parameters to train, and you can have results at every time step. So this could be you measuring the velocity of an object at given times. That could be your experimental observation. And then, knowing the initial conditions, you could then train your network to reproduce the observed values, given the positions which you have at a given time. So X could be then a physical position, which you measure, and you measure the velocity at that specific time. And then you want to extract from the network a prediction for the velocity at each time. Alternatively, you want to have a single output, and this is often used when you do language processing. And in that case, you would skip all these intermediate outputs and then simply compute a final output. And this is something which we called one-to-many or many-to-many last week. So let me just go through that. So when you unfold this one, you can have multi-layers recurrent neural network, and these are all connected, and they feed into the next step, and the next step, etc., etc. So this is what builds up the memory. And it can, if you now keep track of all these weights and biases, which you train at every time step, it means that you can quickly run out of memory if these are large weight matrices. The typical way, so if we just skip some of these because we went through them last time, some of the typical cases which you can end up with are many inputs to one. This is a pretty common in language sequencing. You can have many to many. So these two first ones which you see here to the left, they are typical cases which you encounter either when you are looking at some time series where you can have weather data, or as I said, you're measuring the position and the velocity of an object at different time steps, and you want to find a model which can predict these velocities and time steps at a given time step. And you may just have one type of output. In the code, which we have in the notes, you will find an example of both these cases. So what we are going to do now is actually, I'm going to skip some of these things because this is just a quick reminder, but now we are going to look into the pretty nitty details. So this is where I'm going to test where you're able to stay awake or not. And I don't get offended if you fall asleep, because we have, I mean, some of these equations, some of them are not the most exciting things we're going to do, because essentially it's just us using the chain rule. And then we need to keep track of different dimensionalities of matrices and vectors. But I wanted to just say something. So before we move on here, I wanted to remind you of the type of parameters we have. So we are going to have an output from the hidden layers, which goes in here, and that's compared with your target value, the value you want to reproduce. Now, this introduces parameters which need to be trained. So you would have a coupling between the input. So this could be, as I said, some external probe. Again, going back to this case with the patients you measure the blood pressure of. So this could be you feeding in the blood pressure of that specific patient. And that blood pressure is then being used here. And this Y could be some disease which you have. And you're using the blood pressure to say something about the disease of a specific category of people. And this is then compared with target values. And these are introducing new parameters, which now link this layer with that one. And then you couple the hidden layers from time step to time step. Sometimes, in order to simplify the calculations, what is done is that you skip this coupling, because that can often be the one which is most time intensive and CPU intensive. So you skip the coupling of the hidden to hidden, and you simply give as an input the output value into the next hidden layer. And that means that you can save a lot of memory because you are not making these connections. And often what could happen is that you simply train and reuse these parameters WHH from layer to layer. So often, in order to save space in memory, you train this WHH, which links the hidden layers, for some time steps, and then you stop training and you reuse the same values. Now, one of the things which we also discussed last week was the problem with exploding gradients, which we are coming back to, and vanishing gradients. And particularly this VHH is one of these set of parameters which can lead to exploding gradients. But in general, the input which you would have then to an activation function for the hidden layer would then be this WHX, which connects this part. You have the HH, which comes from the previous hidden layer, a previous time step. And then we have the connection when a little bit later here, we then produce an output, which then is fed into and produces Y. So we produce a C of Y here, which now contains these weights, and this is fed into a new activation function. Okay, so this is basically what we want to do. And the basic algorithm is called back propagation through time. And one of the problems which we discussed last week was the problem of exploding gradients. And I'm not going to repeat everything here, but I wanted to point a little bit to what we will do next week as well. And the problem with the basic recurrent neural network is, one, it's expensive to train. We can also have the problem with exploding gradients. So one way to circumvent that one, especially if you have long sequences of data, is to use something we will discuss next time, which is called long short-term memory. And this has been very popular in natural language processing. So these are different methods which we will say a little bit about next week as well. I do not have codes for that, but we have codes for the standard recurrent neural network. Now, this is a small aside. So many of the codes which you will see here in the different sections which we cover, like the one for RNN, these have often been parts of summer jobs. So if somebody's interested in a summer job in, let's say, this course or for developing course material, just shoot me an email. So the RNN code was something which we developed together with Brage Tenfjord, and some of you may know him. And if you want to get in touch with him, I mean, please let me know. But the same as with the CNN code, that was developed by two students at the IFI. And then we have adapted them to the class here. So if you're interested in a summer job, typically 4 to 6 weeks, developing educational material, essentially software for these classes, please let me know. So this would be more the topic next week, but now I wanted to actually dive into the setup of a recurrent neural network code and the machinery which we need to go through. So I'm going to abuse a little bit on slides here, essentially because there are many things which are more difficult to put on a whiteboard or on a standard blackboard. So let's just quickly repeat some of the things which we know. So an RNN, if you think of a standard neural network, then we have no connections between the hidden nodes. That's the standard setup in a feed-forward neural network. Or sometimes you will see this written as FFNN, feed-forward neural network, because you have a forward pass and a back propagation pass. Sometimes it's just called fully connected neural network, FCNN, but I will often just call it for an NN, a neural network, if that's okay. But this is the basic layout, which you have gone through in different courses. So in the FCN, there are no connections in a neural network between nodes in a single layer. So if you look at these two nodes here, if you take now node, so one, the superscript is the layer, and the subscript is the node in a given layer. Okay? And you see now this is layer 2, this is layer 1, and these two are not connected. Now, when you go to an RNN, this is no longer the case, and nodes in the hidden layers are connected to themselves. And this is normally in a graphical way, is often represented by the curved lines in the figure which you see here. So this will be a single recurrent layers, and then you can have multiple recurrent layers within the same time step. So just keep in mind that this could just be in one specific time step. So let's break these things down, because this becomes important when we want to write the code. So let me just see here if there is a question online. Yeah, this is a very good, there's a comment from people online, so maybe worth mentioning for the LSTM lectures that newer XLSTM seems to perform close to other large language models with substantially fewer parameters. So this is very nice. I'm going to send this as an email to everybody. So if you guys, because as you probably have seen, this is a field which moves at an incredible speed. So when I prepared lectures for last year, I have to revise them every year because there's always something new. So if you come across things like these references, if you come across videos which are pedagogically useful and nice, just send me a link and then I will share with everybody else. Is that okay? Because that's a service to everybody. I've already gotten a nice video on RNNs here, which I'm going to send to everybody. Very good. Thanks a lot. Okay, so now we actually, if you think about the previous message, what we are doing now is actually back to the beginning of the millennium, because many of these things which I'm showing now have been around for close to 30 years, since the end of the 90s. So I'm going to squeeze down a little bit here. Let me just diminish the size. And we're also going to put a full screen view so that hopefully we can compress some of the things here. Can you in the back read well? So if you look at the recurrent neural network, if you now look at the output from a hidden layer, this is fed back into the hidden layer. So you can actually have connections of this type. And this is also fed into the next layer. So compared with a standard neural network, I mean, in a standard neural network, in a given hidden layer, you typically don't have these type of connections. So these can be vectors, but they can also be single scalar quantities. So note that these nodes don't represent the same thing in a feed-forward standard neural network and the RNN diagrams. So in a feed-forward neural network, each node gives a scalar value, which represents a specific feature of the layer, while the nodes in a recurrent neural network, they represent vectors containing all features at that layer. So the connections between the nodes in the RNN are in fact dense connections, as you can see, as seen in a feed-forward neural network. So if you look at this graph here, you get perhaps a better feeling. So if you now think of the type of connections which you can set up, and this would be this layer 2 here, you can have these type of connections. And if you look at this one, you can actually have connections at different time steps. So keep in mind that in a standard neural network, when you look at the properties between different nodes in the same layer, they are normally not connected. So this is a difference. And that will also change the way you train weights and biases. Now you see quickly that when you have an architecture like this, this has the potential to become CPU expensive because you get many more connections and you need to train many more weights and biases compared with a standard feed-forward neural network. So there are some limitations. Typically, the limitations which we discussed last week, one of these is about exploding gradients. And this is something which we have to be careful with. And when you want to backpropagate through the network to tune the weights, but if the input data is a very long sequence, then you have to backpropagate through many nodes. So this is also why the training is often stopped at a certain time step, and then you keep the same weights and biases for the rest of the network because it's expensive to train. And the problem which you have, and which we looked at last time, is, as I said, this problem with vanishing or exploding gradients. So there are ways to make RNNs perform better with long sequences, and the long short-term memory is something which we will discuss next week, which is one possible way of circumventing the problem with long sequences of data. So now that we have reminded ourselves about the structure of an RNN, we are going to look at the mathematics and the type of equations which we have to implement. So let's just set up the basic variables. And so these are the variables which I will use. So you will see now some sequential input with some given features. So which now is going to be represented by different time steps. So you have a time step t here, and this can be an object which now contains, this can be a vector or it can just be a scalar input. That depends on the type of probe which you have. So in principle, this is just a vector with some specific features. Then, if you now look at the hidden layers, I'm going to use a way to address these quantities. So L here, the subscript L, is going to stand for a given node at a time t here. And this is something which then can be represented by a certain set of either matrices or vectors. So we will have a L, uppercase letter L. So L plus 1 is going to be my final output layer. 0 is going just to be my initial input to the network. Okay? So these are just the conventions which we're using here. And this Ni, which you see, can be the number of features in a given hidden layer. And then the output is then compared with the target value. So sometimes I'm going to use a y hat to indicate that this is the output from the network, the predictions you make at a time step. So that means that if you look at the graph here, you will have something like this. So you have these inputs, and then you have the different hidden nodes up to a given layer, L. At the time step 1, this is time step 2. And so these different nodes can then be connected. And then we have the output, and this output is then compared with a target value y at a given time step. But you can also have this many to 1, so you have only one final output at the last output layer. So this is very beneficial in case you have a series of measurements where you observe like the position of a car or velocity of an object, or you measure the temperature and then report the temperature at different days. And then you want to make a prediction on how temperature evolves. You can actually use this to get an indication of whether the temperature in a specific place is rising over time. And there's actually somebody here, is actually down in the corner here, who is actually doing something like this for the projects here. So if you're interested in this kind of analysis and you haven't made up whom you want to collaborate with, that's a possibility. Okay, so this is essentially the part, and so we are going to propagate forward a network, and then we need weights and biases. So these are typically initialized in different ways, but the most common one is to use a Gaussian initialization with random numbers. And in this case, as I said, the zeroth layer and the output layer are going to be labeled either with 0 or L plus 1. And then we need each node to propagate to the node at the next layer, keeping the time step constant, and the next time step, keeping the layer constant. So this is the type of connections which we are setting up. And this figure actually tells you the connections which are being set up in a typical recurrent neural network where you connect all the layers at different time steps. So that means that, and now comes a very exciting part of the text today. So I'm not always, how to say, happy with showing equations on slides. But for the type of topic which we're dealing with here now, I think I found this to be the only possibility. Hope you can forgive me for that. So we are going to have, with these definitions, you could say now, if you look at the first layer, and at the first time step, you have an output from that hidden layer, which is then set up through an activation function. So very common activation functions in RNNs are the ReLU function. But you should try, as always, different types of activation functions. And that depends also on the type of output you want to have. So just to give you an example, we've been running calculations with quantum mechanical calculations with harmonic oscillator type of functions. Then you could actually prepare activation functions which may look like Gaussians. And then you have something which is called the JLU activation function. So sometimes there can be activation functions which favor a specific type of output. So if I'm solving a quantum mechanical problem where a type of harmonic oscillator problem is involved, then I know that my output should be a function which goes like e to the minus x squared. And then you can actually target specific activation functions which favors that type of distribution. That's an aside. But normally people, what they do is they try different activation functions. And then this term here will have weights functions, which then link with the input. So this is the C1. So that produces the output here, which we have, this one. So we have an input here, and that links with the X1, and then there is a bias. And then I'm setting up in the layer here. So it will contain that one, and then I have the time part, which is now my output there. So that means that my C1 of t here is now going to be given by the results from a different layer and at a given time step. And then I have a final output here. And this expression is the same for any hidden node, but for L larger than 2, you simply substitute this x of t here with the output which you have here. So for this one, this gets as an input the x values, but the next one here gets an input from this node at the same time step. And that is indicated in the equations which you see here. And then you would have new weights to train and new biases to train. And then this can be combined to give the final output which you would have. And this final output is then fed into, so this will be the output layer in the first time step. So you can see now how this moves here. If you look at the graph, so you have weights which link the input to the first hidden nodes here. And then you link these nodes with that one. So you have new parameters to train. There is a new set of parameters here to train. And then you continue till you reach the final layer. So this is a set of weights and biases which you need to train for the hidden nodes up to a given layer here. Now, these quantities here link also, or they feed into the next time step and the next time steps and on and on. Does this make sense for the parameters which we need to train? And clearly here, it's pretty common to use the same activation functions throughout. Then we reach the final step here. This is now the output of our training or our model. So the architecture defines the model which we are dealing with. And this part here, the output, is then fed into a cost function. And you will recognize the type of cost functions which we discussed with CNNs and with neural networks. So we're actually recycling the same functions which you have seen before in the code which comes in just a few moments. So you see there's a lot of, how to say, not too exciting bookkeeping. I guess there's not so much exciting things about bookkeeping. except that it has to be done. And in this case here, the bookkeeping is important because it has consequences for the way you're setting up the multiplications of matrices and vectors. Okay, any questions? I see everybody's excited about bookkeeping. This is not the annual conference of bookkeepers, hopefully. So what you end up with, if you now look at one of these specific nodes, you can then write down the type of parameters which need to be trained. So you will have a bias coming in here and the weights coming in. So this is just one specific layer at a given time step, and that produces a new output. And this is the output which goes into the next time step. And this is the output which comes, or the weights which link with the previous layer at the same time step. So you can, if you now look at these connections, you can look at that in more detail. And I don't know if you see this properly here. So let me just put it up like this. So you would then have connections between the different layers. So when you now single out this part here, you can then look at the different types of inputs and activation functions which you have to set up. So hopefully these figures, actually Brage made these figures, and I think they are pretty pedagogical and illustrate the connections between the different nodes. And it's hopefully easier then to see how you need to structure the program. So take some time and look at the slides again, because there are many small details which one may not absorb immediately. Any questions so far? Okay, so let's just move on a little bit, because now comes the time-intensive part. So the feed-forward step, you initialize the weights, you have your input values, and then you just have a feed-forward pass. That's the first thing you do. But then comes the training. And the training is then done by the back propagation through time. Now, as I said, this is a time-consuming algorithm. And you can now see that you can now, if you now have propagated forward through the network, then you have produced some output. So you can do many to many, as we discussed, or many to one. Just to quickly remind you of that, if you look back at what we presented last week and which we refreshed today. So very typical situations are these. So we are just going to look at the general, what we would say, call a general case, that there is an output in each situation. In the codes below, you will see how we can specialize to the case with many to one. So let's go back. So that means that at every time step, or every sequential step, if you don't want to use time, then we have a cost function / loss function, which then compares the value with the prediction which we make with the value which we have observed. And then what we need then is to calculate these derivatives of the weights and the biases. These are the quantities which enter the calculations of the gradients. And that means that at every step, we need to have a gradient for the weights and the biases. And with that, we have a typical gradient descent, which updates the parameters at each layer and at each node which we have in the network. So you would have a back propagation. Here comes a lot of exciting stuff. I may go a little bit quicker through this because it's not perhaps the best way of doing that, but you would typically start with a derivative of the cost function at a given time step, which you see here. So this is a function at a given time step, and it's a function of the output which we have at a given time step. So that means that we need to take that derivative, and that derivative is something which we can rewrite in terms of the different outputs which we have here. this quantity. So this is just a chain rule. So where we simply sum over the possible outputs which we have at the final stage. So L plus 1 is the output layer. So the hidden part can have L layers, uppercase letter L. And it means that we need, when we take the derivative here with respect to these parameters, which then link us with the weights and the biases, then this is something where we have to sum over all the possible values here. And this output Y is actually the derivative, this quantity which you see here with respect to dz, is actually the derivative of the activation function, which we have in the final layer, as a function of the input to that layer. And these inputs will then depend on the weights and the biases. And this is something which we can rewrite in a more compact way. And we can rewrite this in terms of something which is called the Hadamard product. Do you remember what the Hadamard product is for a matrix or vector-vector multiplication? Okay, let me remind you of that. So let's do that, because that's often something which, so let's just go back to the whiteboard. And just quickly remind, so if we take a vector, suppose we now have a vector x of t, which now is given by x0, x1, and up to element xn minus 1. Then we know that the inner product, just to remind you of that. So the inner product is then normally written like x transpose times x. This is just for the vector itself. And that is simply a sum from I equals 0 up to n minus 1. And then I would have the xi squared values. Okay, that's the inner product. Then, if I do a vector times a vector, I can also have the outer product of two vectors. So the outer product is a matrix. And that's often written like x times x transpose, like that. And you can quickly see that if you now do a simple example where this vector is given by a quantity, let's say x0 and x1, then the outer product becomes a 2 by 2 matrix. So that's going to be given by, so this will have x0 times x0, and then there's going to be x0 times x1, and then I have x1 times x0 and x1 times x1. So these are typical operations which we do on vectors and matrices as well. And outer products and inner products are probably things which you have seen many, many times. Now, the Hadamard product, on the other hand, is something which gives us a compact way of writing out element by element multiplications. So if we now look at the Hadamard product, this is, if we now take two vectors, so let's take a vector x, which has 3 elements as an example, x0, x1, x2, and then we have a vector y. So we just write it like that. And then we have a y0, y1, and y2 here. So when we look at that one, and it's often written like this, of y, this is the same as us doing a element by element calculation. And that's given by x0, y0, x1, y1, x2, and y2. So that's an element by element multiplication. And that's called the Hadamard problem. Now you have to be, sometimes when we are looking at the way we encode it in Python, when we encode it in Python, if we do the inner product of two vectors, then we would typically in Python write it like X transpose T, and then it's multiplied with X. So this should be the alpha. This is the way you would write the inner product of two vectors. If you write X times X in Python, so if you do this one, on the other hand, X times X, this is actually the Hadamard. That gives you an element by element multiplication. Just a small reminder, because it's so easy to make that error. I've done it many times because I'm just multiplying two vectors, and intuitively you would use that symbol, but that's actually the element by element multiplication. Okay? Okay, you've been extremely patient here, guys. You really deserve a good break, because the type of approach which we do today is more to go through the equations and set up the structure which we need for writing a code. Should we take a small break? Is that okay with everybody? Okay, for those of you online, I'm gonna stop the recording here. So we take a small break in 15 minutes and just be back then. So welcome back to my second attempt to put you all asleep. So I didn't succeed in the first lecture. So let me see if I can do better now. Okay, so the thing which we discussed before the break was the setup of the different derivatives and the type of derivatives which for those of you who have written a neural network code in courses like FYS SDK4155, you have seen this type of operations where we have the derivative of the cost function at a given time step, derivative with respect to the outputs, and that is something which we can then rephrase in terms of the derivatives of the activation functions. And then we are going to break down the derivative of the activation function in terms of the different weights and the biases. So we're just going to step ourselves down from this term, which you see here, this final term here, because this will depend on the Z's which we have, as we had for a standard neural network. And so we have to implement the chain rule. There's some small notes here that the derivatives may sometimes, if you think of a feed-forward neural network, then they're often real numbers. But sometimes they can be vectors, and sometimes they can be matrices. So just keep that in mind. So the kind of notation here may switch between scalars, vectors, and matrices. So we have not included a specific notation for that. So there is another note here. There are a lot of indices to keep track of. So in order to make the notation a little bit simpler to follow, we will use L for layer, and with L being the final hidden layer, L plus 1, uppercase letter L plus 1 is the input to the cost function. That means the output from the final sets of hidden layers. You have several layers with indices L1, L2. There's a given time step, and then we will have the subscripts for vector matrix elements, number of input features. So just to remind you quickly of that, I mean, the input could be just one single thing you're measuring, like you're measuring the blood pressure of a patient. That could be just one feature, but you could actually have many more features which are plugging in. So this person or this patient, if you want to use that as an example, you could actually look at the blood pressure, you could look at the oxygen content in the blood, etc., etc. So you could have many features which you feed in at a given time step. So that means that this X, when you feed that in at a given time step, that could be a scalar, but it could also be a vector of many observations. Sorry, not observations, but many features. And then you also have the number of features in hidden layers. So we'll not always write the upper bound of summations explicitly. So, but in general, what you would have then is, if you look at a summation like this, it's a summation over the nodes from the previous layer. And you see that because that contains the output from the previous and then multiplied with the weights and the biases. So when you take the derivative to perform the derivations, we often shorten this set of equations into just one parameter delta. And that's exactly the same thing which we did when we did set up a code for a neural network. And this has become a kind of standard way in the literature to denote the derivative of the cost function at the final layer times the derivative of the activation function with the input to the final layer. So that's I guess you remember that output or that parameter for those of you who wrote your own neural network code. And then from this parameter delta, you can find the gradients with respect to the output bias. Note that some of the weights and biases occur several times in the recurrent neural network. So you have to sum over the different contributions. So I don't know how interesting it is to actually go through many of these details, but the different derivatives which we need to set up are the derivatives with respect to these weights, to these weights. So these are the set of derivatives which we need to set up. And all these derivatives will then be calculated through repeated usage of the chain rule. So what you see here is a typical application of the chain rule, so that you link the outputs here. And we know that this function C here depends again on the weights and the output from the previous layer and the biases here. So this is how you can explicitly see where the bias comes in from here. So that's just one typical example. And when you look at that equation, this is something which then simplifies into Kronecker delta. So that means that for that specific form, it's actually much easier. And then finally, you just sum over all the time steps here. Then similarly, you would use the chain rule for the weights. And in that specific case, it's again, you setting in the expression for C here. And then you have this set of equations. And then you take the derivative with respect to one of these parameters. And this is exactly in the same way as you did when you wrote your own neural network code. So it's essentially a repeated implementation of the chain rule. And if you wish to be a little bit arrogant, the chain rule is something you saw back in high school, right? I guess most of you did. Or perhaps even in kindergarten, eh? If you study in high school languages in China and Japan, you have to take mathematics at an advanced level. Okay, that was a digression. But anyway, this is not the most exciting thing, but I've collected all these terms so you see the equations which we are going to implement in the codes. I'm going to skip some of these things here because it's not so exciting to look at all these equations. But here is a type of diagram which shows the back propagation through the output layer. So you're doing this going backward. So you have the output layer, you calculate the derivative here, and this propagates down all the way down to the different nodes which you have here. So these are the type of derivatives which we need in the explicit setup of the back propagation through time. Then, if you think of an arbitrary node, you can set up the equations which you would need. So if you look at the derivative of the cost function with respect to an arbitrary node, you can then dissect it by just looking at the graph which you see here. So let me just reduce it a little bit. because then if you look at this specific node, these are the typical quantities which you need to evaluate. Now, you see quickly why the back propagation through time, if you want to train it on a long sequence of data, that this becomes computationally expensive. So ways to shorten down all these type of calculations are things which people are actually working on. So this is active research. And this long short-term memory approach is one way to circumvent all these gritty, nitty, detailed calculations which we are setting up here. But if you just look at this one, you see clearly all the types of derivatives which we need to set up. And that becomes quickly time-consuming. The code which you will find down here actually sets up these derivatives for the different types of nodes. So I may be skipping some of these details here because this is not the most exciting thing. The thing which is a little bit more interesting to look at is actually the functions which we have implemented now. So this is a kind of, if you want to write your own code, please feel free to use these examples here. And the whole idea is to show you what is actually behind the curtains. And clearly the implementation here is the back propagation through time, which is normally not the most efficient way of training a set of sequential data, in particular if you have lots of data. So we need to define some functions. And if you go back to what we discussed in connection with CNNs, and also for neural networks, you will recognize many of the functions here. There is one thing which you need to think of. And this is something which applies to essentially all codes you're going to write, if you write them from scratch. And this is the usage of a library like JAX, which includes automatic differentiation. So for those of you who have followed a course like FYS STK4155, automatic differentiation is the thing which saves the day. And previously this was included in a Python library, which is called AutoGrad. But now it has been, the development of AutoGrad has been discontinued, and it has been replaced by JAX, which also has vectorization built in and just-in-time compilation, which normally speeds up a Python code. So I recommend taking a look at that, but there are some small problems in the calculations of the gradients, which we are coming back to. So there are some, the way JAX vectorizes the variables is something which we need to pay a little bit attention to. But the activation functions which you see here are the same as those as which we had in the CNN code. So you will recognize many of the ingredients from that code as well. And here there are some of the standard ones, the sigmoid, the softmax. This is the gradient of the softmax because we had some problems with JAX and the softmax. There's a ReLU, there's the LReLU, the leaky ReLU, the TAN-H, and you can add more functions. And a function which is very popular now is this GLU, which distributes which actually gives you a Gaussian distribution. And that may work better in some applications. But as I said, often it's pretty common to actually try different types of activation functions. Then we have the cost functions. And here I took the cross entropy and the standard one for the mean squared error. So these are things which you have seen again. But types of cost functions are things which you can change. This is a log reg. And then we have the standard cross entropy, which we typically use for either binary classification problems or multi-class classification problems. And this is something which you probably remember back from different calculations. Now, the thing with JAX and automatic differentiation then is that JAX is extremely efficient. So for the ReLU and leaky ReLU activation functions, which are not continuously differentiable, we actually handle this explicitly. So when you look at derivatives, we typically use JAX for most cases. One thing you need to pay attention to with JAX is that the grad function is not in itself vectorized. So this is a small, drawback with JAX. So that means that if you send in an array to a function that has been differentiated, JAX will treat this as a function with an array as input, not as a function treating each element individually. So you can see that with this example here, if you have f of x, x squared, then the gradient, it returns the gradient, and we put x equal 2, the gradient should be 2 times x. So that means 4. So that gives the correct value. But if you try to input an array of values, what you get then is an error. So a gradient only defined for scalar output functions. And this had the wrong shape. So this is because JAX does not treat each element in X individually. And to get around, there is a vector map function in the JAX library, which vectorizes the function. So this is the way you would circumvent it. So if I now introduce this array of 10 points from 0 to 3, and I want the derivatives, you see now that this gives us the correct derivatives. So with 10 points, we know that from 0 to 3, we should get something which is equal to 3 here. The derivative is 2 times x. So we should get 6 at the end point here, which it does. So just keep that in mind. There's also another drawback. It only vectorizes in one dimension. So if you have an array which contains several axes, so like in this case here, then you would need to input VMAP, VMAP, VMAP here. So it's not optimal, but people are working on ways to circumvent it. But this is something which we have to live with till now. Okay, these are technicalities. Then if you just scroll down here, you will find the schedulers, which are the ways we update the learning rate as before. And this is the same as you have seen in FYS but also in a discussion on the CNN code. So if you go back to week 5, you will see the same type of functions which were included there. So we have the schedulers where we have a constant learning rate. We have momentum, gradient descent with momentum. We have adaptive gradient. These are just some of the ways to update the learning rate. Adaptive gradient with momentum, root mean square propagation, and also the Adam way to reset the learning rate. So this is as before. And now we need to implement the RNN code. So the code is now going to contain a set of classes. So there's going to be the complete network of several layer objects. There's a layer class. There's an abstract class which contains information that is shared across the different types of layers. And it is the parent class of input layer, recurrent NN layer, and the output layer. And then dense layer, which is a fully connected, used to switch from a recurrent network to a regularly fully connected network. And this is especially used for non-sequential output. For instance, when you are dealing with a classification, where you want to classify the entire sequence with a single output. So when we are coming back to this many to one, this is a functionality which you will find interesting. Then there is a node which contains information about a single node. This is where all the mathematics of forward and back propagation is actually collected or takes place. So this is actually in this node quantity. So I hope you now have a kind of top-down view of it. And if you go through the different equations which I put up earlier, then you can quickly see what is being coded where in the program. So in the code, you want to be able to input batches of values so you can feed forward and back propagate many inputs at once. So that means that typically the input to the network will therefore be an array, typically with 3 axes. The input axis separates different inputs, then the sequence axis separating the different time steps, and then the feature axis. So these are things which we need. So always when we're developing a program, we need to think of the flow of data. So we will, as I said, if you are looking at a different category of patients and you want to observe which factors are important for the developments of a stroke, then we know that high blood pressure, diabetes, obesity are important features. So you could then think that every time step when you gauge a specific set of patients, you measure the blood pressure, you check for diabetes, and you check for obesity. And then obviously you would then see whether these patients at a given time step have developed a stroke or not. So these are actually the 3 most common markers for developing a stroke, sadly. So I hope none of you will be exposed to that, obviously. But this could then be the features, the feature axis. We would have 3 features in the input, and that separates different inputs, and then you could do this at different time steps. So this is a typical way by which you could structure your data. And since the RNN class is dependent on the layer classes, and the layer class is dependent on node class, we will build a network from the down up. So this is a bottom-up type of approach, starting with the node class. So this node class takes actually care of the math, which we discussed in forward and back propagation. So I'm just restating the equations here. So there is the input to a specific node with information from the previous layer. And this quantity here will then have information from the previous time steps, which you have here. And then it would also have from the information at the same time step. So that means that the final input, so if we just scroll back a little bit to this image which we looked at a given node. So let's just go back a little bit, because this one explains everything which takes place inside the node. So we will have an input which comes in here from the previous layer, and then we get from the previous node here. And that is used then to generate an output from this one, which then feeds in here. So this given node is now depending on these weights and these biases. It also has information about the output from the previous time step. And similarly in here, we need information about layer L-1, and we also have the biases from that step. So these are the type of quantities, the mathematics which we need into the node class, because that's where we plug in the mathematics of the feed forward and the back propagation. So these are just the equations which we need then to set up in the node class. So I'm just refreshing them here. And the input and output from a node are typically 2-dimensional arrays with different inputs along the first axis and the features along the second axis. And the equations for computing forward and back propagation assume that we are working with column vectors. But when you perform a matrix multiplication, it's pretty common then to actually take the transpose of the matrix. So in the code here, we've actually performed the calculations in this specific way. So where n now is the number of inputs. And note that these have switched places in the matrix multiplication, and that W is essentially a transpose of the corresponding vector W, or the corresponding matrix W. So it's not a big change, but you can be taken into account by reversing the order of some of the matrix multiplications. So these are the typical quantity which we set up, and they are set up in the code which follows here. So it should be pretty well documented. So you could follow the examples which you see here. So I'm not going into all the gritty nitty detail here, but I invite you to take a look at the code if you want to use this. It cannot compete with TensorFlow. It cannot compete with PyTorch, unfortunately. So if you're thinking of speed and you want to use these ready-made libraries, this is normally what we recommend. But if you're interested in developing your own recurrent neural network, then feel free to use this as an example. So I'm just going to go quickly through some of these things because this is not so exciting. So this class consists of something we call a layer class, or several layers of various types. This is an abstract class which keeps track of attributes and methods that are common for the different types of layers. And this contains now different functions where we are setting up the different parameters, the features. This resets the weights. It defines the schedulers. It updates the weights of all nodes. So this class actually is a kind of more overarching class, which then sets all the different parameters which are needed. And then there's an input layer class where we define that as discussed previously. So we are sending in a three-dimensional array where we now define the size, the sequence length, and the number of features as input. So that's the input layer class. You can take a look at that one if you want to. And then there's the RNN layer class, and that represents the recurrent layers in a recurrent neural networks. And it takes the value at each time step in the preceding layer and computes the output from each node in its own layer. And it propagates forward for each node one by one. And then it does also the backward propagation. It goes through each node in reverse order, inserts the gradients of the cost function with respect to their output, and lets the nodes calculate the gradients with respect to weights and biases, and then uses these to update the weights and the biases. So in this code, we have not allowed for an option where you can actually stop training the weights and reuse them throughout the network. So this is functionality which would be needed to be implemented. We also have not implemented the recipe we discussed last week for the case of exploding gradients. So this is obviously an initial skeleton. And if you want to add things like dealing with exploding or vanishing gradients, this is something you would have to set up. There is also not possible to actually truncate the training of the weights and the biases. So this is not set up here. So I wanted to, after all this discussions from my side, I wanted to show you, after we've gone through the output layer, so I wanted to say a little bit about the way we can run these codes. And the output layer, there is a option in the code where you can run this for many-to-many, as I said. So this is the many-to-many case, or just the many-to-one case. So these are the two options which are baked in. So that means that you could use this, for example, in language sequencing. It's pretty common, or for sentiment analysis, where we want to determine if a sentence has a positive, negative, or neutral tone. So that means that you would then structure your data so that you would just have one type of output. This is also used in case we want to do a classification, as you will see later here. If we are training, let's say, a differential equation, recurrent neural network, which trains on data from differential equations, then we would have at each time step a specific output. So then we would do the many-to-many type of training. So these are the two options which we have baked in the code here. So let's, I'm going to skip some of these details here because the dense layer here is actually something which deals with the way we deal with the, whether we do many-to-many or many-to-one. So I'm not going to go through everything here, but I wanted to show you some implementations of this machinery here. So this is actually what you're seeing now is the full network. And I have done some runs before the lecture started, so I just wanted to discuss them. So this is just the full code here. So there are three applications. One is on the weather data. And if you're interested in that, there is actually here we have taken the data set by a course which has been developed. And you can find this data set from here. And in that specific case, what we have is the max and the min temperature, where it's been raining, and then the Tmax the day after. And these are the different time steps. And in total, there's something like 13,000 entries. So that's the data set we're going to train on. So the relevant columns, which we are training on Tmax and Tmax tomorrow. So we're only going to use these. And note that the data set has 13,000 roughly time steps, which is actually too much. So we will quickly run into exploding gradients the way the code is set up. So we are just going to retrieve only the first 100 rows. Because also else, if you run this code, you will just sit and wait and wait and wait. And since it's such a long sequence of data, there's quickly the risk of having exploding gradients, which is something which we have not included in the codes here. So this is just us preparing the data. We have a validation set. So for the validation data, we retrieve a subset of the data at some later time, such that the training and validation do not overlap. So we have a validation set which contains 70 time steps, even though the training data contains 100 time steps. So the RNNs are pretty flexible when it comes to input the data sets. So the results here, so we use scikit-learn, we scale the data, which you should always do. You use the min-max scaler. So the data has been scaled, and then this is the way you would set up the code. So you define the cost function. So now we are fitting the mean squared error. There is no hyperparameter in addition to that in the codes. So for this specific code, if you want to add hyperparameter, you would have to do that. So this is not included, the hyperparameter training. And you see now that typically what you would do, so the activation function for the hidden ones are the identity function, which is normally used when you want to output a data where you're fitting a function. And the scheduler, we use Adam, and there you see the learning rate, which is 10 to the minus 3. We create the neural network, so you call the function RNN, you add the input layer, and in this specific case, we have one layer and one layer for the output, and then we reset the weights. And then you train the network on the data, and then the thing you have the input data, the time steps, and then the validation sets, number of epochs, number of batches, and then we have the lambda parameter, which we just set. We actually, in this case, we only have a lambda, so it has a possibility to do a lambda training. I forgot that, sorry. And then the number of epochs, and then we extract the output. And typically here you would see a kind of a training error, which, let me see now, there's a question online here. Yeah, that is correct. We use no sampler to subsequence training sets. That's correct. So it's an error which is pretty decent. It's not optimal, but it's okay. The error on the training decreases and stabilizes as it should. So if you look at the output here, you will see something like this. So this is the dark one is the target value. And this is the fit which we had with this network. And it has an error, a mean squared error 1.59, which is not so bad. It's not optimal. You would have to train with more hidden layers, more nodes, etc. You can do the same for the validation set. And for the validation set, you also get a decent reproduction of the data. So you could say this is a kind of decent fit. The problem is if you want then to extrapolate to data where you did not include this is what you will get when you extrapolate. And in a certain sense, this is expected. It is expected because your data are very much jumping up and down. But what you could see now is that there is a trend in some kind of increasing temperature. So if you were to do this over long times, and I think down in the corner here, there's somebody who has done it, and you can see a gradual increase in the temperature over time. But if you want to make this kind of day-to-day prediction, where you can have large fluctuations, this is perhaps not the best method to use. So perhaps the result is what you might expect. Now, the case which I am typically dealing with is more the solution of differential equations. So if we just skip this one now, so let's just go down to, this is just another way to display the data. This is what we discussed last week. So in that case, we were looking at the solution of a differential equation with harmonic oscillations. We are going to put an external force equal to 0. So this is going to be an object which oscillates back and forth, but then it has a damping term, which is proportional to the velocity. And this damping term is the one which you see here. So in this specific case, what I'm doing now is to define the parameters of the differential equation. And this is the equation which I'm solving. So I'm actually setting in this term here. That's the driving force now, which contains the harmonic oscillator piece, and then a damping due to a velocity-dependent term. So this is the equation which is needed when I'm setting up the derivative for the velocity. So in here, we can then use the Euler-Kromer method. So instead of me giving you observations, I'm now taking the solution of a differential equation with the Euler-Kromer method as my observation. And what I want now is to have my recurrent neural network to train on this data and make a prediction. Now, this is a case which is going to give us oscillations with damping. And normally when we do that, we can often get pretty good results with recurrent neural networks. And this is something you will see when we now train the network. So we can set our network and train it on a differential equation. So we use a position as input for each x. So that's the input. So I have solved this equation numerically with an Euler-Kromer, which is also not the best method. But then I use the positions which I get as an input to the network. So the x's. And then the thing I want to reproduce is obviously the velocity. So this is the answer provided by Euler-Kromer. And then you can see now that x, so x is given by the input to the model, y is the target output. And then I simply set up now and I want to reshape to fit to the RNN. And I'm setting up my learning rate, my hyperparameter, and then I do the scheduler. It's a pretty simple network, just so that it can run quickly through it. And if I plot the results, the arrow you will see now as a function of epochs in the stochastic gradient descent is diminishing. And if you look at the prediction which we make, this is something which is closer to what we may expect. This is still a pretty light network, so I can add more layers, etc. And then my training would obviously become better. But you can see now that the true values, so we've been training the data on a few data points. So essentially beyond the time 10 here, we're actually making a prediction. And it's actually pretty good. And this is just a damped oscillation. So at a certain point here, after some time, this will just stop on. But you see the power of the RNN, that what you could do then, suppose now you have a complicated differential equation solver, and then you would use that complicated differential equation solver for just a few time steps. Let's say up to here, because that's time consuming. And then you would train on the data from your favorite equation differential solver, and then use that data to train a recurrent neural network and then extrapolate. In this case, I made a comparison with all the values because the differential equation solver is actually pretty simple. So this is one of the typical examples where you would use a time series in order to make predictions beyond where you have measurements. And if you have this kind of oscillatory motion or regular motions, then you can expect a recurrent neural network often to do a pretty good job. There's a final example where we, again, let you go through the handwritten digits. So this is a case of many to one. And the data set is this, the famous one, which you have seen. And here we're just importing the data set. So we have 60,000 images with 28 times 28 pixels. Now, using an RNN is normally not the best thing to do for this type of applications. So if you look at the convolutional neural networks, these are typically the favorite methods which you would apply on this type of problem. So in this case, we have a training set with 60,000 images. And so to speed up the training, we're just using a subset. So we're just using 1% of the data set. And this is essentially because else it would actually take too much time here. So the target values are integers from 0 to 9, but we will need them in a 10-element arrays with a 1 in the index corresponding to the number and a 0 else. And here we are setting up the training set, etc., etc. And then we are plotting, these are the data which we are plotting, some of the images which you see here. And then we can build the RNN model and use that to make a prediction. And again, we are training with a data set. We have a pretty simple and shallow recurrent neural network. We can actually make this more and more complicated and deeper, but this is actually a pretty simple one. And the cost function now is this logistic regression function. The activation function is a softmax, and we also run with the ReLU function. And then we train it on the MNIST data set, and I can show you some of the results. So the training error is actually not so bad, and the accuracy is well, it's not optimal. We're taking a much smaller data set, a shallow network. So in principle, we would like to have an accuracy which is 100%, but here we're just getting 60%. So this is actually not very optimal. So the model successfully predicts 52% of the digits, and this isn't very much. So feel free to adjust the parameters. But this time we can. So it just see what our model is predicting here, and these are the type of predictions, and you can see now that what it should have predicted. So here it gets a 1 or 2. Here we should have a 2 here, but we're getting something which looks like a 6, etc., etc. So the predictions are not optimal, and this is not how you would use recurrent neural networks. If you do if you apply convolutional neural networks to this problem, you would typically then end up with an accuracy which is close to 99 to 100%. So this is, in a way, it's taken as an example to show you that RNNs are not exactly what you would use for image classification. They don't do a pretty good job there. But for the type of problems like this with the differential equations, this can actually be a very powerful method to extrapolate beyond the points where you have data for. Okay, so we are getting close to the hour. Next week, I want to say a little bit about the long short-term memory, and I'm going to send to you the update from one of the people online here. And then after we've done that, that will be probably the first lecture next week, we are going to go into autoencoders, which is a very popular way for reducing the dimensionality of a problem. Now, when we do that, we also need to discuss a widely popular method for dimensionality reduction, which is called principal component analysis. So we are going to look at principal component analysis and autoencoders. And when we are done with that, we will most likely start with generative methods and look at those for the rest of the semester. Any questions? I hope I didn't put you to sleep, guys, because this is not, I mean, going through many of these chain rule operations is not always the most exciting thing. But I hope you see the wood for the trees and the basic mathematical elements which you need in order to write a recurrent neural network code, if you want to do it.